So now that you have the hang of integration and how to basically take the area under a graph, let's look at something a bit more complicated called improper integrals. And improper integrals are basically an extension of the integration you've already been doing, but including limits in it. Improper integration. Okay, so before we jump into improper integration and this first example that I want to show you today, I first need to sort of give you the intuition for an idea that is going to be really useful for understanding improper integration. So let's say we have the function f of x equals 1 over x squared. And if you were to draw this out, you would get a function that looks something like this. And then what if I asked you to draw the function for me f of x equals 1 over x? You would get a similar graph, of course slightly different, and it would be a hyperbola. And if you think about this, it should be really easy to see how if you square this function, you get this function, and how all the negatives should become positives essentially. But now what if I asked you, with this graph, I want you to take the integral, or I want you to, let's not even use integrals. What if I said, I want you to find the area under the graph from 1 to infinity? So that's essentially all of this area here, all the way to infinity. And then I want you to do the same thing for this one. I want you to find the area under the graph from 1 to infinity, all the way there. So your probably first intuition is going to be that this integral of 1 over x dx should equal infinity, right? If we're going from 1 to infinity, it should be infinity. And that's what I would think too if I saw this for the first time. Because you have an amount of area that's under a curve, and this amount of area is forever increasing, and thus you would just expect for it to go to infinity. And in this case, for the function f of x equals 1 over x, you'd actually be right about that. This does go to infinity as you take the integral from 1 to infinity. However, the same cannot be said about this, 1 over x squared. If we were to do 1 to infinity of 1 over x squared dx, you'd actually get a number. I don't know the numerical value off the top of my head. We'll calculate it by the time we finish this. However, this will be some number. And it's important to recognize why it will come to some number. Because at first, you might be thinking that's absurd. As this continues to go on and on, you're just going to see it add more and more area, right, to the sum of area. And so let's sort of look at why this might be true. And the fact is, it all centers around this idea of the fact that this equation, 1 over x squared, is decreasing at such a fast rate compared to the function 1 over x. And that's because of this x squared, of course, in the denominator. It's making everything smaller. But what we're seeing is this is a possible situation, right? If you did 1 to 1,000 of this integral up here of f of x dx, maybe you get something like 3.11. I don't know if this is the actual value. But then if you took the integral of 1 to, let's say, we'll add an extra 0, so we'll get 10,000 of the same function f of x dx, maybe what you're getting is 3.11. And maybe it's the case that every time you multiply this value, the final value of the integral, the right value of the integral, by 10, all you're doing is adding on or a smaller version of 0.1, maybe with more zeros in front. So you're just adding some small amount to the number. Well, what will happen as you do this over and over again, as this number becomes just bigger and bigger, tends to infinity, you're just going to see smaller and smaller numbers being added to it. And when smaller and smaller numbers are added to it, this will continue to get incrementally larger, but it will never get larger than 3.11 repeating. Can you see how that happens? Because the size that it's incrementing this final count of the area under the graph is not large enough to affect any of the previous digits. It's only adding on new digits per se. And this is just one way of thinking about it. There's many ways to think about why this is actually happening, but this is just one of them. And as you do more of these problems, you'll gain more intuition for understanding why it works like that. So with that in mind, let's try to figure out exactly how much area is under the graph from 1 to infinity of 1 over x squared. So we'll just write an integral, and we'll do 1 over x squared, 1 to infinity. And right here, this is the exact definition of an improper integral, because it has an infinity in one of the bounds. There are many other improper integrals, but this is the main example of them. And this is not really something you can do for the most part. And so what mathematicians have done is they've used limits to do the same thing. So instead of saying we're going to take the integral, or the area under the graph, from 1 to infinity, they're saying we're going to take the limit as a variable t tends to infinity of the integral 1 to t 1 over x squared dx. I forgot my dx over here. And so essentially this is what this is saying, is that we're going to see how this or exactly what a limit does. What does this look like as we move this right bound, maybe the right bound's here, as we move it closer to infinity? What is it going to look like? And so we can actually solve this. The key to solving these is actually to separate these into two different problems. First, into finding the integral, and then afterward, finding the limit. So we'll continue writing the limit as t goes to infinity, but instead we'll include the integral in a different color. And many of you may not actually be used to this at this point, of having a variable as one of the integration bounds, but this is actually something that's completely valid to do and is often done. For example, let's say you're just a normal person who wants to figure out how, I guess you're trying to do a normal problem is what I'm trying to say. And you want to see how the area from 1 to a certain number x changes. Then you could put x or some variable up here to get a function, a resulting function that allows you to move around this right bound easily. You'll gain more intuition about what that means as you do more of these problems. But doing this integral is super easy. We'll just say equals the limit as t goes to infinity of, if we do this integral, we're going to increase this exponent by 1, and so we get negative x, negative 1, and that's going to be evaluated from 1 to t. We're now going to, I should really be switching up the colors more, sorry about that. But now we're going to do this again. T goes to infinity, and we're just going to plug in t essentially. So this is going to get us negative 1 over t. Hopefully you saw how I did that. And then we're going to do minus negative 1 over 1. And so, oops, I deleted too much. So then this gets us the limit as t approaches infinity of, first of all, let's notice here that we have a negative negative, so this just becomes positive, and this is just 1. And using limit rules, we can separate these two things and just have this in the limit, because this is the only one with t. This has just become a plus 1, and so then this can just be plus 1. Right? Does everyone, hopefully you see how I moved from here to here using limit laws. And then we can look at this limit here and try to evaluate this. And this shouldn't be too hard either if you remember how you do your limits. as t tends toward infinity, this is just going to get smaller and smaller and smaller and smaller until this goes to 0. And so this limit is 0. Essentially, we end up with 0 plus 1, and that means our answer is just 1. So that's pretty interesting. That means we're saying that if you take the area under the graph from 1 to infinity of 1 over x squared dx, the area under that graph is just 1. I think that's pretty cool and pretty an insightful thing to do.